What about you? And in this one, we're going to look at pulse width, modulation, and duty cycle, and all that jazz. There's a whole load of videos on YouTube that cover this subject, but there's very few that I can see that really go into it with any real depth. Okay, so there's a PWM controller and it's on a throttle body, and we'll click her on and we can see in the background our waveform, and we'll increase it up. The duty cycle goes up, the pulse width widens, and we're controlling our throttle body, our butterfly flap there. But in truth, the throttle body doesn't work like that at all, but that's just for a visual demonstration. Well, it does work with PWM, but it's not linear like that, because that is really a stepper motor. But we'll just do a recap on PWM. Okay, I'm going to go through this step by step in this video, so if you skip bits of this video, it mightn't make much sense. But I'm going to start at the start. I'm going to start with the old school way of doing it, which is the analog. And we'll have an analog setup here with a potentiometer that I'm going to use as a voltage divider, and it's powering this wee LED, and we can see we're controlling the voltage to control the wee LED. So what I'm going to do, I'll just take it down to a sheet of paper here, is so we start at 0. We're going to bring the voltage up to a maximum. In this case it's 5 volts, and then we're going to bring it down again, back to 0 again, and then up again, hold it there for a moment in time, and then back down again. So we'll get what looks like a sine wave. So that's fine. So I'll just take that away for a second and bring it back up. So this is our potentiometer, and we're going to screw it up, and we'll see the voltage increasing. And as we do that, the wee LED is starting to light. So we're controlling the brightness of that LED by bringing the voltage up. Simple as that. Now, I'm using an LED here deliberately because this potentiometer can't take an awful lot of current. So if you're wanting to drive a motor or an actuator or something that moves, that takes a bit of current, you need a very beefy one of these. So that is the reason, one of the reasons why we use PWM. And we can see the milliamps there, over there. It's practically nothing. It's very, very little to make this LED light. So that is going up and down there with respect to time. So the time is me screwing the knob on the potentiometer, going up and down and up and down. So that's fine. So PWM then can be described as getting an analog output, which is an output like this, from a digital source. So what we mean by that is, we're getting our marker pen. So what we can do is we create our the square wave that we're familiar with, and so we start off with 0, we'll go up to an on time, and then we'll go off to an off time, we'll go up to an on time, off, and repeating like that. So that's our square wave. Now with pulse width modulation then, we'll have an on time here and we'll have an off time, and that part of the waveform is known as the period. So if that was equal to that, we would say that would have a 50% on time, 50% off time. So that's what we call the duty cycle. So it's 50% on, 50% off. So that would have a 50% duty cycle. And this measurement here then is the pulse width, the width of the pulse, and that's measured in time. So it depends what the frequency is to what the pulse width actually is. measured in time. So the period, the pulse width, and the duty cycle, and then the number of pulses, or the number of these occurring per second, is hertz. So that's the frequency. So we'll just change this setup, and we'll get our controller out again. Right, we're back with our PWM controller here, and this is set for frequency in hertz, and it's going to read kilohertz. So it's going to say it here on the mixer, but you probably can't see it there. And we can see current, and we're lighting a 12 volt 501 bulb there. So if we screw this up a wee bit, we can see the frequency is 11.63, and that is 11.62 there. That is kilohertz, so that is 11,500 hertz there. And if we just change a wee setting here, we can see that is the duty cycle in percent, so that's 47.8%. So that's roughly about half there, and we can see that on the waveform with our square wave. And I'll just knock the cursors off there, so you can see the square wave there a wee bit better. And that's increasing 62, 75%. So you can see 75% on time and 25% off time there. And we're controlling the brightness of our bulb by increasing and decreasing the duty cycle. So that's fine. So the main components then of our pulse width modulation is frequency, and that's in K8Z, so it's in thousands of hertz. So we're going to go into why we need such a high frequency, and the duty cycle and the pulse width is the control. So how does this actually control the thing, and why do we use PWM? So we're going to get into that as we go along. So the frequency is quite high, at thousands of hertz, and we'll go into that's very important. So what we're doing is, the frequency is usually set. The frequency is usually so if you saw there, it was 11.5 kilohertz, and that didn't change. It was in around that, but it didn't change. Now there are systems that can start off with, say, 2,000 hertz, and then it'll jump up to, say, 10,000 hertz or something like that. But it's in thousands of hertz anyway. Normally it doesn't change. Normally that stays fixed. So that stays fixed. The other thing that stays fixed is the voltage, because what this is doing, what the control is doing, is changing the current flow. So the current flow increases and decreases, and that's what is controlling our motor actuator, but in this case it's a wee bulb. So the voltage remains fixed, so it's constant. In this case 12 volts, and the frequency normally remains fixed, but if it does change, it doesn't change linearly. It doesn't just increase in increments. It'll just jump to another, level. So anyway, okay, let's see that. Let's see if that's true here. So we've already measured the frequency. We see it stays stable. Let's see if what I'm talking about with the voltage is also correct. So there's our duty cycle increasing there. We know that our frequency stays stable, but this voltage is increasing at increments similar to the analog signal, and it's not doing what I said. So if we change the voltmeter to a graphometer, we can see there it's sitting 9.68 volts. I'll just move that wire there, and we'll bring it down 8 volts, 7 volts, 6 volts, but the peak here is 12. So this meter is reading the average voltage. So this is where you can be caught out with if you're testing and you're testing a pulse width modulated signal with a voltmeter using voltage, you will see a strange voltage, perhaps, because it's taken the average or an RMS value of a reading there. So I'll just zoom you in that wee bit. Okay, so maybe you can see side here, that's 8, and so the peak is at 12 here, but the reading is 8, but it's still peaking at 12. And if we screw it up, we'll screw it down even, it'll show you even better. There it's reading 4 volts. So you maybe put your a voltmeter on that, and you think maybe that's a signal wire or something, because it's only going to say 4 volts, but it's peaking. It's actually peaking at 12. So your voltmeter is that could confuse you. That could throw you astray if you're testing in a real world application. So I'll just show you those scope readings a wee bit closer, so you can see the frequency staying the same and the voltage staying the same on the scope. So here's our scope capture, and as we can see here, the frequency stays 11.65 like we saw on the frequency meter and the yellow meter that we saw, but up here 12 volts, constantly 12 volts. Here's the duty cycle 52, 58, and that's the duty cycle of the on time. This is the duty cycle of the off time, so that's a negative in front of that, you can just about see it, and that's the pulse width there in microseconds. And so frequency remains the same, voltage remains the same, constant, which is contrary to what we saw on our voltmeter. So if you're testing and you discover strange voltages like that, you want to maybe flick your meter on the frequency, and if you see a frequency, you'll know then you're on a PWM signal. So to explain why the voltmeter is showing 4 volts, 5 volts, or whatever on a what is a 12 volt signal, well, the voltmeter, as I said, is taking an average, or it's similar to an RMS, a root mean square. So we're going to just talk about an AC sine wave. Now this is AC here, so it is a bit different. So an AC sine wave, now it's going to look a bit like our analog signal, but I'll show you why it's different. So that's an AC sine wave there. But the difference is that the zero line is in the middle, whereas before the zero line was at the bottom. So 0 was at the bottom, but in this, so it goes plus and minus. So UK household voltage, if you put a voltmeter into a plug, it'll read 240 volts. But that is the RMS value, which stands for root mean square. So that is a mathematical function that you take the square root of the mean and then you square it again. That's what that means. So an easy way to work it out is it's 0.707 of the peak. So 0.707, say roughly 3/4 of the way up the wave, so roughly about here, then it's going to say 240. So that's a peak, and that's a peak. Now this is a reason why you don't put your scope and scope the mains. So I'll just show you that. So here we have our test leads plugged into the mains. Now these are special test leads. These are fused leads. If you notice, they're thicker there. So that's what I use with mains voltage, and 241 volts, 240 volts. And if we do the same frequency test, we see 50 hertz, not kilohertz, just hertz, 50 times a second. And we can even look at the duty cycle, and it's 50%. So it's half and half. So if we look at our AC waveform, so that equals that in time, and that is occurring 50 times a second, but 240 is 3/4 of the way up the peak, what we're reading. So you can work out the peak mathematically, dead easy as well. So get our trusty calculator out. So we know our RMS value is 240, and we multiply that by the square root of 2. And that comes out at 340 volts. So our peak there is, what am I doing, pen? Our peak that waveform is 340. We're measuring 240, and this is because the voltmeter is measuring on the RMS value, the square root of the mean and squared again. So if you want, in the DC terms, it's the average value. So our output that we're reading over there is the average value. It's a bit like what's going on here with this. So just on a side note, I said don't scope your mains voltage. And you might think to yourself, well, I have a 21 on 10 meter. I'll even if it is 340, I can multiply it up. Here's a 20 to 1 on 10 meter. I'll stick that on it. Well, I'm going to show you why. AC voltage, it's not the magnitude of the voltage. Yes, you could step it up within a 10 meter and make it so that the scope can handle it. But AC is different from DC because it is equal and opposite in the minus value. Your attenuator is a voltage divider. There's a couple of resistors in here and it reduces it down to 20, but it only does that in the positive. If we bail out the negative, it's straight through. So the negative, so you would get minus 340 volts straight through into your scope. And if you have a scope that is connected to a laptop, here's one here, for example, real budget job, but even a Pico 4425 will be the same as this. So that negative is connected right through. So the negative is common across it, unless you have a differential scope. A differential scope has the negatives are separate. So this negative here is common throughout the whole thing. So the negative on your USB that you're connecting to your laptop, if I can hold that on there, is through on your laptop. So you'll be putting minus 340 volts into your laptop on the USB. So don't recommend that. That was just a wee side note. I need to get back to pulse width modulation. So hopefully that's the voltage explained. The next bit is the frequency. Why do I need such a high frequency, and what is the effect of if it was a low frequency? So I need to set up something. I need something that I can change the frequency from, because this has a fixed frequency at 11.6 kilohertz, as we saw on the scope. So here we have a wee signal generator that will output a changeable frequency, and we can change the duty cycle here. Its output's very, very little, so it'll light a wee bulb up. So as we can see, I have it set 001 on the frequency and 001%. So if you can see that, okay, there's it there. So if we put our wee voltmeter on here, we could jump to that. Well, we know now that looking at the voltage on the voltmeter, it's not going to be correct. It's jumping all over the place at the minute. But what we are interested, because it's a PWM signal, is the frequency in hertz, and it's showing there just shy of 1 hertz. So whenever I have a very, very low frequency, we can see the bulb is flashing. So it's on and off there. And we can see that over on our mix sig there. So if we bring this up, the frequency, we'll bring it up that wee bit. There's very, very little current flowing, as you can see. So there's 3 hertz. We'll get up to 4 hertz, 5 hertz. Our wee bulb is flashing a wee bit quicker. We'll get it. We'll bring it right up. We'll get more. We get more captures on the screen there. More signals. So we're up to 11 hertz at the minute, and we're still flashing like crazy. So if we bring our duty cycle up, and we'll change that over to duty cycle here, there's it at 1. So that is what it says there as well. So just bring it back into that again, and we'll bring that up, and we'll see our pulse width over here getting wider. And what's our result? Our wee bulb's flashing, still flashing like crazy. So if we have too low of a frequency, we do not get a constant output. So if you're trying to control a motor or an actuator or something like that, it's not going to move. It's not going to move nice and smoothly. So too low of a frequency is no good, and that's why it needs to be a way up. So still flashing there. We'll get the frequency up a lot more. We're still on 11. We'll get it. I'll put that back to frequency again. 27 hertz. And the wee bulb, well, it's nearly constant now. It's still flashing though. Oh, it's more or less static there now. It's still flashing a bit. And we can see more pulses on the screen. And we're sitting 39 hertz. We'll bring the duty cycle up, and it's still flashing. So that is one example of why we're using the high frequencies. But that's not the end of the story. There's another very good reason. And if you noticed that whenever we're doing that, whenever we're bringing the duty cycle up, that increased the current flow. So even though we're still at a pretty low frequency, we're still at 39 hertz there. When we bring the duty cycle up, we'll see the pulse width widening, but the current increases. So that's what I was saying with this. So we're controlling the current flow, not the voltage. So up to now, we've been using PWM to control a light bulb or an LED. But what if we want to control a motor, like in an EGR valve, or what we saw at the start was this stepper motor off the throttle body. So the bulb here is purely resistive. Resistance changes probably because of the heat and stuff like that, but it's purely resistive. But the motors have other components in them. Okay, when I say components, what I mean by that is, so our bulb is purely resistive, so we'll have a resistance. But a motor will have inductance in the form of the winding, and it'll probably have a bit of capacitance. So in between the windings, you'll have insulation, and that'll give you a wee bit of capacitance. So this is a typical RLC circuit. So resistance, inductance is noted with an L, and the capacitance is C. So these two components here, the inductance and the capacitance, are known as the reactive components. So those two together are reactive. This is just resistance, so it doesn't have a reactance at all, apart from changing the voltage, as we saw in our wee potentiometer. So this inductance that we'll have, especially in a motor, anything we are winding on, is an inductor. So we're going to discover the problem with having inductance. So if we put voltage across the inductor, that's fine. Okay, so what happens is we get this thing called a back EMF. So what happens is whenever we put a voltage across that inductor, it creates a magnetism that tries to stop the flow of current that is actually creating it, and that is known as a back EMF. So EMF standing for electromotive force, or otherwise known as a counter motive force. So it counteracts the current that's creating the coil being energized in the first place, and that's known as Lanza's law. So a quick demonstration of that is we've got a copper bar and we slide a magnet down it. So what's happening there is the magnetism in the magnet is creating a current in the copper bar, and that current is preventing the motion of this magnet from sliding down the copper bar. So it is impeding the motion of the magnet coming down. So these three components together in a circuit is actually known as the impedance. So we're all used to the equation V equals IR. So that is a purely resistive calculation, a calculation with a circuit that's purely resistive. If we include these other two components, it's V equals I, and we use Z, and that's the way I do my Z's. So Z being impedance. So if we pulse our signal on and off, that then cuts down or prevents this back EMF from rising, which is what is opposing the current flow. So it doesn't get a chance to rise across in this inductor. So that is if we turn it on, turn it off, turn it on, turn it off, this back EMF current doesn't get a chance to increase, which is what we're wanting to eradicate, and that prevents the opposition to current flow. So there we go, that's about it. Hopefully that has described all that a wee bit more. Some of the components of PWM, the frequency of the duty cycle, the voltage remains constant, the frequency usually stays constant. It can jump up, as I said, it's in thousands of hertz to prevent the back EMF, and what we're actually doing is controlling current flow. So there you go, that's a wee recap. And yeah, if you've stuck it out this long, many thanks for watching. Hopefully you got something out of that. Hopefully that'll help you with whenever you're testing on a car in the real world situation. So again, many thanks for watching. All the best, and bye bye.